Okay. So we take example in which we have to use the division algorithm to prove that 3k square minus 1 is never a perfect square for any integer k belongs to z. Okay. We prove this by using method of contradiction. Okay. So we have to prove that 3k square minus 1 for k belongs to z is never a perfect square. This we have to prove. So we prove this by contradiction. We prove this by contradiction. Okay. If possible, suppose that if possible, suppose that 3k square minus 1 is a perfect square. So 3k square minus 1 is a perfect square. Then we know that square of any number. Okay. We know that square of any integer is either of the form 3m or 3m plus 1. Okay. That is 3k square minus 1 is equal to 3m or 3k square minus 1 is 3m plus 1. This is of this type. Let us take 3k square minus 1 is equal to 3m. We find out value of m from this. So this gives me m is equal to. What is m? Here m is again belonging to z. M is the integer. Now we take first if this 3k square minus 1 is of this form. Okay. So if 3k square minus 1 is 3m, then from this m equal to 3k square minus 1 upon 3, or this is k square minus 1 by 3, where k belongs to z. Now since k is in z, k square is also an integer. Okay. And minus 1 by 3, so we can find that it is of the form it cannot be a non-negative integer. Okay. So here this implies that, or if second case we can consider 3k square minus 1 equals to 3m plus 1, and this gives me this one which take this side, so 3m equal to 3k square minus 2. Okay. If I take this 1 to this side, that becomes minus 1, minus 1, minus 1, minus 2. So 3m will be this, or this gives me m is equal to 3k square minus 2 upon 3, or this gives k square minus 2 by 3, where k is integer. Now in both the cases, we can say that this is not integer value, because this is a integer minus fraction. Of course, answer will be in fraction. So you will find that in both the cases, answer is in fraction, means m is not belonging to z. So in both the cases, we are not getting m as a non-negative integer. Okay. So then m cannot be a non-negative integer. Then m cannot be a non-negative integer. M cannot be a non-negative integer. So for all k belongs to z, which is a contradiction, because m is an integer and you are getting it cannot be an integer. So this is a contradiction. Which is a contradiction? Which contradicts to m belongs to z. Which contradicts to m belongs to z. Hence Our assumption is wrong. Hence our assumption is wrong. Thus 3k square minus 1 cannot be a perfect square. Okay. Thus 3k square minus 1 is never a perfect square. Thus 3k square minus 1 is never a perfect square. So this completes the proof of this result. Okay, now let us take another example. So we take now another example. Okay. So here we are going to prove that. Okay, question was like this: prove that no integer in the sequence 11, 111, 11111 and so on is a perfect square. Now to prove this, we are using again the result which we have been proved in the last lecture, that any square of any integer is either of the form 4k or 4k plus 1. This we have proved. Okay, so here in this case we are simply going to prove that the terms of the sequence are of the form 4k plus 3, because it is not 4k or 4k plus 1, that we are going to prove. Now here we have 11, we can write 11 as 8 plus 3. 8 means 4 into 2, so 4k plus 3 where k is 2. Similarly 111 can be written as 108 plus 3, and 108 is nothing but 4 into 27, that is 4k. K is 27 plus 3 and so on. So I can write the in general the terms of the sequence of this sequence in the form last 3 digits as 108 plus 3 is equal to 4k plus 3, because this number is of the form 4k for some integer k belongs to z and so on. Thus we can say that each term of the sequence is of the form 4k plus 3 for some k belongs to z, and 4k plus 3 is not representing any perfect square. This 4k plus 3 is not a perfect square, because if the integer is a perfect square, then it is either of the form 4k or 4k plus 1, and as 4k plus 1 or 4k is not equal to 4k plus 3, therefore we can say that the given sequence of integers like 11, 111 and 1111 and so on is not a perfect square. So thus we can say that there is, so thus we can say that, and hence we can say that no integer in the sequence 11, 111, 1111 and so on is a perfect square. Okay, so this completes the proof. So here in this example we have to show that 1 by 3 into m square plus 2 is an integer for all m greater than or equal to 1, where m is an integer. Now as there is a 3 as a divisor, so we are assuming divisor as 3, considering 3 divisor and using the division algorithm, we know that every integer can be expressed in the form 3k plus 1 or 3k plus 2, that is known to you. So by division algorithm, so we are using this. So to prove this, since are considering 3 as a divisor, using division algorithm, we show that any integer m has the form 3k plus 1 or 3k plus 2. So here we substitute values of m in this form and we prove for all the 3 cases. Okay, so first case, let m is equal to 3k. If I put m equal to 3k in this expression, then 1 by 3m into m square plus 2 becomes 1 by 3 into, what is the value of m? I have to substitute 3k. So m is 3k into 3k square is 9k square plus 2. So you will find 3k will get cancelled, the k is inside. Okay. So you will find that this is equal to k into 9k square plus 2, which is belonging to z. So this is an integer value. Now come to second, let us take m equal to 3k plus 1. So then again we show this 1 by 3 m into m square plus 2 is equal to integer, that we have to prove. Okay. So 1 by 3 into m is here 3k plus 1. So wherever there is m, you just substitute 3k plus 1. It's in the form of square. So I use the bracket, square bracket plus 2. Okay. So whole square formula we can use, and we can write it is 1 by 3 into 3k plus 1 into, now square of this is 9k square plus 6k plus 1 plus 2. Now 2 plus 1 is 3, and again you can find 3 is common from that bracket. So taking 3 commons, 1 by 3 into 3k plus 1 as it is. 3 taking common, this gives me 3k square plus 2k plus 1. So again you will find 3 will get cancelled, and this belongs to z, which is an integer. So there is no term in the denominator, means it is an integer. Next, come to the third case. Let m equal to, so let us take third case. Let m equal to 3k plus 2. And again we find out 1 by 3 m into m square plus 2. That is 1 by 3 m. M is 3k plus 2 into m square means 3k plus 2 whole square and plus 2 as it is. So this gives me 1 by 3 3k plus 2 into bracket whole square formula 9k square plus 6 to the 12k plus 4 plus 2. Again you will find 4 plus 2 is 6. Again you can take out 3 common and rewrite it as, so I can take 3 common and I write it as 1 by 3 3k plus 2, 3 common from bracket, so it is 3k square plus 3 for the 12, so 4k plus this is 6, 3 to the 6, so 2. Okay. So again 3 will get cancelled and remaining is a integer, and thus we have shown that in all the 3 cases m is an, whether m is 3k or m is 3k plus 1 or m is 3k plus 2, in all the cases we have shown that 1 by 3 into m square plus 2 becomes an integer. So this means 1 by 3 into m square plus 2 is an integer for all m greater than or equal to 2, greater than or equal to 1, where m is an integer. So this completes the proof of this example. Okay. Now let us take another example. So next example is the example from competitive exam also. So let us take that example. Now in the example we have to find out number of 2 digits which have the property that when they are divided by sum of their digits, the quotient is 7. Okay. So if you look at the example, you will find it difficult, but this is not very difficult. This is very simple. So we have to find out how many such 2-digit numbers are possible, having the property that whenever these 2-digit numbers are divided by the sum of their digits, and it gives the quotient is equal to 7. So let us take 2-digit number, and we know that any 2-digit number is having unit place digit and tens place digit. Okay. So I can write it is of the form 10a plus b, where a and b are the natural numbers. Okay. So we know that we can express any 2-digit number in the form. So let a 2-digit number be, let a 2-digit number be 10a plus b, where a and b are natural numbers. Okay. So we can write this in the form, and a is not equal to 0 also, because if a is 0, then it becomes a one digit number. Therefore, a is not equal to 0. Now, by the given condition or by the given property, what is given? Given property is that if this number is divided by its sum of the digits, so digits are a and b, their sum is a plus b. The quotient is 7, so this gives me equal to 7. I just simplify. I take this to this side and I can write 10a plus b is equal to 7 times a plus b. Okay, or this gives me 10a plus b equals to 7a plus 7b. Okay, or from this I can write 10a minus 7a is equal to 7b, and this to this side minus b, or this gives me, this is 10 minus 7 is 3a, and this is 6b. So dividing by 3, it gives a equal to 2b. Now I give different values for b starting from 1, and I can find the values for a. So if I put b equal to 1, what will be the value of a for b equal to 1? A equal to 2 ones are 2. So a equal to 2. If I put b equal to 2, this gives me a equal to 2 2s are 4. Okay. For b equal to 3, this implies a equal to 3 2s are 6. Corresponding numbers will be then 10a plus b will be equal to. So corresponding numbers I can write. The corresponding two digits number. What is 10a? 10a means 10 into 2, that is 20, plus b is 1, that is equal to 21. Or I can simply write ab means 2 1 21. Similarly here I can write this number will be 10a plus b will be 42, then 10a plus b will be 63. Okay. Similarly, if I substitute the values for b as 4, what it gives for b equal to 4, this you will see that this is the table of 21. Okay, first value is 21, second is 42, 21 2s are 42, 21 3s are 63, 21 4s are 84. So a will be 8, then 10a plus b is 84. Next value will be more than that, because if I put b equal to 5, a will be 10. So this is beyond the two digit number, because it will be 105. Okay, 10 and 5. So 100 and
which is not a
two digit number, and therefore what we will do. So what are the values now? Whether it is satisfying the condition or not, I will see. Okay, let us see this satisfies the condition or not. If I divide 21 by sum of the digit, what is the sum of the digit of 21? What is the sum of the digit? 2 plus 1 is 3. So 21 upon 3, is it 7? Yes. 42, 4 plus 2, 6. 42 upon 6, is it 7? Yes. 63, 6 plus 3, 9. 63 upon 9, again 7. Okay. And 84 upon 12, because 8 plus 4, 12. So 84 upon 12, again 7. So we'll find that all these numbers are satisfying. So there are only 4 numbers, 4 two-digit numbers, 21, 42, and 6. How many two-digit numbers is the question? So how many two-digit numbers are there? 1, 2, 3, and 4. So there are 4 two-digit numbers satisfying the property that the two-digit number divided by sum of the digit has the quotient 7. Okay. So this is the answer. Okay. So thus there are 4 two-digit numbers 21, 42, 63 and 84 satisfying the property that when they are divided by sum of the digits, the quotient is 7. When they are divided by sum of the digits, the quotient is 7. This is the answer. Okay.